All right, so find your notes for 1.2. We're going to go through, the video will follow right along with the notes there. You can fill them in as you go. So 1.2 is on functions and their properties. So you've seen a lot of this before already. Function notation, if you have an equation that's y equals 2x plus 3, you could write that in function notation, which would be f of x equals 2x plus 3. The f of x and the y are interchangeable. F of x means that that's a function, so it's more specific. It's going to pass this vertical line test that we'll talk about in a minute. Two things that you have with a function: you'll have domain, which is your input values. Typically, it's your x values. You'll have the range values, which are your output values, typically your y values there. So when you put in an x value, what do you get for the y value? And you've seen this before many times now. So quick review. Vertical line test, an equation is a function if you can draw a vertical line anywhere along the graph there and it only touches the graph one point at a time there. So that first one is a function. Second one, same thing. If I draw a vertical line anywhere, I have some sharp points on here. Doesn't matter. This vertical line can only ever touch this graph at one point at a time. So both of these are functions because they pass that vertical line test. However, this one over here, if I draw the line over here, I'm okay. But once I draw it here, it hits my graph twice, or in the middle here, it hits it 3 times. So this is not a function. Fails that vertical line test. It means for each of these x values, this particular x value back here, and it looks like -2, I have 3 different y values. Or over here at 0, I have 3 different y values that go with that same x value. You can only have one y value that goes for the x value. So the x's can't repeat. That's a fancy way of saying that. So domain and range. Domain we just talked about is all the input values or the x values typically for the function that where the function's defined. Some functions may have restrictions on the domain. So this example here is area of a circle. The radius can't be 0 or a negative value, or you don't have a circle there. If you had square roots in the problem, if you have a square root, say it's x, this number underneath the square root has to be greater than or equal to 0. If it's a negative value, we can't take the square root of that. If you have 1 over something in the denominator here, this something in the denominator can't equal 0. So those are things that you have to be concerned with when you're talking about the domain. Those values can't be 0 or negative to make that function. All right, so for example 3 here, we're trying to figure out what the domain for these different ones are. You can look at these in the calculator. A lot of times for domain, you can kind of think about what that domain is going to be without having to graph the problem there. So if you look at letter C first. This is area for the equilateral triangle. So A of S is the area, S is the length of the sides. So if you think about this, the length of a side, in order to have an equilateral triangle, you'd need something that's positive there. So for this, your S has to be greater than 0. I would say it can't even equal 0 because then it's not a triangle. We're going to put these answers in interval notation just to review that. So how do you say S is greater than 0? Well, the lowest value S could be would be 0, not including 0, so parentheses. And the biggest value S could be, well, it would head to infinity, but never actually reach there. So that's our interval notation. So if you look at letter A, I'm going to write it down here so we have a little bit of space. This was a radical problem here, and we said that that number underneath the radical can't be negative. This is not in the denominator, so if you take that radicand, the number underneath the radical, that would have to be greater than or equal to 0. So x has to be greater than or equal to -3. So if I write that in interval notation, the lowest value x could be would be -3. The bracket means it includes -3, and then we're going up towards infinity there. So that's letter A. And then letter B, we have a few things going on with this one. So let's see, for B, I have a square root in the top, and I have an x minus 5 in the denominator. So let's look at this in pieces. So if you look at the square root of x part, the restrictions on that domain, that x is going to have to be positive or 0, so greater than or equal to 0. So interval notation, that will look like this. So from 0 to infinity, including 0. But the only problem is in that interval there, if I include 5, that denominator is going to equal 0. And I don't want that denominator to equal 0. So I have to say that x can go from 0 to infinity, we'll say excluding x equals 5. So that's how I would write that interval notation there. And that's good enough for that. So that's domain. Domain you can really think of algebraically. You can also look at it, like I said, in your calculator and see what values you can plug in for x type of thing. Range is a little bit harder to do, and I usually do range with a calculator. So let me pull this up here. Let me clear off this stuff. So let's look at this first one. So I have y equals 2 over x. So we'll put that in. And then I'm going to look at the graph of this. I just reset my window to go from -10 to +10. So if you look at this graph, there's our graph there. Looks like two things are happening here. So it looks like if x is equal to 0, we'll have a vertical asymptote. X can't equal 0 because that's going to be 2 divided by 0, which is undefined. So that vertical asymptote at x equals 0 doesn't want to be right on the calculator. Here. There we go. There we go. So if a vertical asymptote at x equals 0, that would affect the domain. If you look at the other direction, there's never going to be a value for y that's going to equal 0. There's no number that I can plug into this function and get this outcome here to be 0. 2 divided by 2 would give me 1. 2 divided by -2 would give me -1. If I plug in 0, it goes to infinity. So there's no way I'm going to get 0 out of it. So it's a horizontal asymptote. And we'll look at how to find horizontal asymptotes in this chapter as well. So my range then for this one, so domain, might as well do that one. Going from left to right, starting at the left here, the graph goes to -infinity. And then it comes up here and gets real close to 0, but it doesn't actually touch 0. So I need a parentheses on that. And then it starts up on the other side here, and the positive part goes from 0 to +infinity. So that's my domain. The range is going to look very similar to that, because the range going from bottom to top, the graph here goes down to -infinity, and as I start at -infinity and work my way up, the highest part it goes to is 0, but doesn't actually touch 0. Then it leaps over that asymptote there, and then it starts out really close to 0 and goes up to +infinity. So for this one, the domain and the range happen to be the same intervals there. Right, so if you're looking for range, I would put it in the calculator. I would look at the graph of the calculator. Range is bottom to top. How far down does it go? How far up does it go? Boundedness sort of ties into that idea of range there. So if a function is bounded below, it means that it goes up to +infinity. It has a lower bound, goes down to a certain value, goes up to infinity. If a graph is bounded above, that means it has a high value, but it doesn't have a low value, so it'll head to -infinity. And then if a function is just bounded, stated as being bounded, it means that there's a highest value and a lowest value that's not infinity or -infinity. So if you look at this first graph here, this has a low point here. It's not going to go any lower than that. So it has a lower bound, which means it's bounded below. If I had a parabola that opened up, downward like this one would be bounded above. And then for this letter B, these kind of just keep getting close to 0 there. I have a low point, I have a high point. These tails are just going to keep getting closer and closer to this x-axis here. So this one is bounded on both sides there. It's never going to go higher than this point or lower than this point. So they'll just call that bounded. Okay? It's not going to have an outcome that is, let's see, this goes from -1 to +1. It's never going to have an outcome that's out of that interval there. All right, so let's ask you a couple questions about boundedness. And then the last thing, odd and even functions here. A couple of ways that you can look at odd and even functions. If you can use your calculator, the easiest way is if a function is a special function, it might be an odd function or it might be an even function, or it may not be either one of those. It may just be a plain old function. So for a function to be even, one thing that you could look at is symmetry with the y-axis. So any graph that you look at that has symmetry with the y-axis, where if I fold this graph along that y-axis there, the left side fits right on top of the right side. It could look like this. It could look like something like that. All right, so that was supposed to look even on both sides there. But you get the idea there. So you can, let's see if I can make it better. Oh, not much better. You get the idea. So if you fold along the y-axis there, the one side will fit on top of the other side. Numerically is a little bit harder, I think, to see. Numerically, you're looking at your x values. Positive and negative of the same x value there gives you the same y value. Positive 2 and negative 2 gives you the same y value. Positive and negative 1 gives you the same y value. Algebraically, and we'll look at this, means if you plug a negative in for x, you end up with the original function, or I like to say, no signs changed. The function looks exactly the same as what you started with. So we'll look at those. We'll go through an example so you can see what that means when you plug a negative in for x and you get that outcome where no signs changed. For an odd function, when we plug that negative in for x, we end up having the opposite of the original function, which over here is going to mean that all of the signs change. So anything that was positive would become negative, anything that was negative would become positive. So if you have your calculator, you can look at the graph. I think that's the easiest way to do that. Graphically, what happens is we have symmetry with the origin. And what symmetry with the origin means is if I turn the graph upside down, right side up, it looks exactly the same. So you're kind of using this as like a fixed point there, like a propeller blade. If you turn it on that fixed point there, the graph looks exactly the same. So upside down, right side up, looks the same. And then numerically, if you look at, I don't like this very much, but positive 3, negative 3, you had negative 27, you get the opposite, positive 27. Negative 2, positive 2, the outcomes are the opposite there, and so on. So I usually either do it algebraically or graphically. I don't usually do the numerical table type of thing there. All right, so what do you have to do to determine this? So two things you do. Look at the graph in your calculator. If I'm letting you use your graph, your calculator for this next test, you would be able to do that. If not, odd, even, neither, what we're going to do for all of these is we're plugging a negative in for x. So in your function, you're going to take out x, replace it with negative x. And we're going to see what happens. So if I take negative x and raise it to the 4th power, that's going to give me positive x to the 4th, times that 3 out in front would be 3x to the 4th. Uh-oh, it's getting funky on me. The next term there, if I raise negative x to the 2nd, would be positive x squared, times 5 would be 5x squared, and negative 7. If you look back at this original function here, your f of negative x, when you plugged a negative in, we got the exact same function that we started with there, which means this function is an even function. Right? None of the signs changed there. This 3x to the 4th is still 3x to the 4th. 5x squared is still 5x squared. Negative 7 is still negative 7. So this particular function holds that property where it's an even function. The second one, if we try to plug in negative x, and we simplify, negative x raised to the 3rd power is going to stay negative, so this would be negative 4x cubed. Negative x times negative 7 will be plus 7x. And then again, look back at that original problem there. Positive 4x cubed is is now negative 4x cubed. Negative 7x is now positive 7x. So all of the signs changed. Which is just an easier way to say this. When you plugged in negative for your x, you got the opposite of the original function. Makes this an odd function. So now every function doesn't have to be an odd function or an even function. You could have a neither. And if you look at this last one, if I do the same thing by plugging in negative x, negative x squared just stays x squared, so this is 3x squared. Negative x times 2 would be minus 2x minus 1. If you look back at that original, some of these signs changed, but not all of them. 3x squared stayed the same. 2x is now negative 2x, so that one didn't change. And then the positive 1, negative 1 and negative 1 stayed the same. So not all signs changed. But some of them did. So if not all of the signs changed, it can't be odd. None of the signs change, so it can't be even. So this is just neither. If you look at a graph like this, it doesn't have symmetry with the y-axis. Y-axis is over here. If I look at this graph right side up or upside down, it doesn't look the same. So it doesn't have symmetry with the origin, it doesn't have symmetry with the y-axis. So it's just neither. It's still a function. It's just not one of these special odd or even functions. So that's what you're going to look at in the homework problems, and you'll check those solutions then with my solutions online.